Saradi, can you hear me?
Yeah. Yeah.
Okay. Okay. Let us start this webinar now. Yeah, just 2 minutes ahead.
Yeah.
Okay. So, well, good evening, everyone, and thank you for the participants who have joined till now. Welcome to the online webinar hosted by Four Vision Instruments and Bruker together about the technical webinar on advances in Piezoresponse Force Microscopy, PFM. In India, we generally capture a huge demand on this research field to characterize the electromechanical properties of piezoresponsive materials at a nanoscale. So this PFM has become a powerful tool to study the local electromechanical sample responses in ferroelectric materials. So then we decided to broadcast through an engaging webinar about the technological advances from Bruker nanosurface. Our speaker today would be Dr. Yogesh Jairam, and I am Ravi Teja. I am the moderator for this webinar from For Vision Instruments Private Limited as the Indian representative of Bruker. We are proud to celebrate the For Vision's 25th year as an established company, and we are here for the solutions of nanotechnology and microscopy. So, as I told you, we are the channel partners for Bruker Nanosurface, who are the leading manufacturers of surface and dimensional analysis tools. Well, before I introduce the speaker, let me make a few logistical comments. We appreciate your participation, and we shall have the question and answer session at the end of the presentation. So in the meantime, you can use the questions or chat box session to put your questions, and we would analyze them. I request all the attendees to mute your microphones for the reasons best known. We shall try to progress. Definitely, we have this recording available for this webinar, and we can share it individually once the webinar is accomplished. Now, let me introduce my speaker, Dr. Yogesh Jairam, the Key Accounts Manager, Bruker Nanosurface Division, and positioned at Chennai. Dr. Yogesh is responsible for application development and technical support of surface metrology and tribology instruments. His academic background was in solid-state physics and material science. He obtained his PhD in KU Leuven, Belgium, working on linear and nonlinear optical effects in metal nanostructures. Prior to joining Bruker, Dr. Yogesh was a postdoctoral researcher in University of Toronto. He has published in over 15 peer-reviewed international journal papers. He has also presented at many international conferences. He's here to present the technical talk about the implementations of PFM through Bruker. Dr. Yogesh, over to you.
Thanks, Teja, for this nice introduction. So good afternoon, everyone, and thanks for joining us today for this talk. So the presentation that I have is an overview session on different PFM implementations in Bruker AFMs. So I will go through some of the highlights and some of the different technologies we have in this front. So before we start, I would like to start with an overview on the Pfm principle, then talk about, the conventional Pfm imaging for vertical and lateral, and some spectroscopy and Pfm nanolithography. Then we will talk about three exciting things in this area that's like simultaneous PFM that's correlated with, current measurements or cKPFM measurements. And then we have this switching spectroscopy to eliminate the electrostatic effects that you might see in your PFM data. And then we talk about the DataCube PFM. So people who have done PFM, know that PFM is some kind of what we call like a indirect electrical technique, right? So what you actually do is you apply a bias and then that is translated into this piezo response from the materials, and then you're going to get a tip deflection or a change in the volume of the material, which is actually what you detect, as opposed to like direct electrical measurements like conductivity, where you apply a bias and you have some circuits and you measure the current, right? So this is an indirect way of doing it. So the way it's achieved, it's so you have this cantilever, give you the laser. So you have the cantilever, and you apply a bias between your cantilever and your sample. And this cantilever is the conducting material. It's in contact with your probe. Then you apply a AC bias, either on top of a DC bias or just as an AC bias, and at a fixed frequency. And then this elicits an piezo response from the material that will push the cantilever up and down at the same frequency as your bias. And we can use a lock-in amplifier to lock on to the signal, right? So you can have in-phase response or out-of-phase response. You also get the phase response here. So that will tell you a little bit about the way the polarization of your domains are in your material. So this is mainly for domains that are orienting normal to the sample surface, right? So you might also have in your sample domains that are on parallel to the sample surface. So those will bend the cantilever, so you will have some kind of torsional response of the cantilever, and that's how you detect them. There are, of course, the PFM data. In ideal cases, only the PFM data. But when you apply a bias between a conducting material probe and the sample, there are a lot of electrostatic effects that can come into play that can affect your data. So that is something that we are, people have been trying to get around it to get the response, piezo response, pure way, so without the electrostatic component of it, right? So there are different ways to doing it, and we will talk about it as we go through today. So these are some of your typical PFM data. So you always get the height image. So you get the topography, and this is the BFO sample, and you get the amplitude of your piezo response on the phase. The phase tells you about the polarization of the polarization direction of your domains. Amplitude tells you a little bit about how strong these domains are, right? So that is what it is. So you apply a fixed bias, and this is a fixed frequency for the entire image. You fix the frequency, and then you can image it. So here is again the polarization relaxation. So you have a pre-polarized film, and then you continue to image it with your piezo, and then there is some relaxation of the piezo, the polarization, and you can see some regions where they are flipping back to their native states, so to speak, right? There are, of course, some high sensitivity PFMs are required. So sometimes your sample piezo response is not high. So then either you can use a 16x gain. This is inbuilt in our system to get a higher to signal to noise ratio, or you can run your PFM experiment at the contact resonance. So when we speak about contact resonance, is the resonance of your cantilever on the sample, right? It's contact point. That's the contact resonance. And there you can do it. So operation at contact resonance, of course, requires you need to track this contact resonance. The contact resonance will change from location to location due to the domain changes or also even topographical changes, and then you can do it. And we can also, of course, do some frequency sweep. So now we are talking about applying a fixed frequency for your AC modulation. You can do a sweep, and you can do this kind of get the resonance points, and then you can do something called the cRPFM mode, which we will also talk a little later in the presentation. With these new systems like the dimension icon systems, you can measure both. We have multiple lock-ins, so you can use the lock-ins to either look at the vertical or horizontal or both at the same time, right? So here you can see, in this case, you have the height image and the vertical response and also the horizontal response at the same time, right? So this is something that we can do. And there are many works in this area. So something that I would like to highlight is one from the Nature Communications, which is very high high voltage image. So then you can see they are doing at both vertical PFM and the lateral PFM of a different bias voltages, and they are capturing them. Okay, then you get the spectroscopy. So in spectroscopy, you have this amplitude response, so which is ideally looks like this. So you have two two peaks. One is for this way, and the other one is for the reverse sweeping. So you sweep the bias voltage, and then you plot the amplitude response at a given point. So in this case, it's done at multiple points, and then there are multiple graphs corresponding to that. So the system has a very low drift that allows you to stay in one position as long as you want. You can do repeated measurements. You can do imaging, and then you can do this response at particular area. Then, of course, you also have this hysteresis loop. So the hysteresis loop again, so this is like, okay, you sweep from -10 to 10 and then back again, and then you see this hysteresis from the material. And this particular example is also with and without an external magnetic field, right? So in this case, they had this nano-patterned multiferroic material at room temperature. And then you can see when you apply different magnetic field, how the PFM behavior changes in this material. Okay. We also have the Pfm spectroscopy, which we have significantly expanded in the recent days. So to give you an overview, so we talked about PFM being affected by the electrostatic the signal from your sample or noise from your sample. So this increases also with the DC bias, right? So you apply AC bias or also a DC bias to your sample, especially when you're sweeping or something like this. So then you also have the work function, which is the work function difference between your tip and your sample. In ideal cases, this should be 0. Then you don't have any electrostatic signal. But when you apply a very large DC bias, or like sometimes you might need to do, then you have a large, significantly high contribution. It's directly proportional to that, right? You have a large electrostatic signal. So the one way you can get around it is like using like a stiff cantilever. But the problem with that is if you're using a stiff cantilever on PFM is done in contact mode most of the time. So then you can have significant sample damage or the tip damage. So the one way the people do it is like you record your PFM signal at two different intervals. One is called the write point and the other is the read point. So in the read point, you want to make sure that the DC bias is as low as possible, ideally the negative of your work function difference, right? So then you're going to get 0 electrostatic. Then the data you get is directly quantitative and you don't have any electrostatic components, so you can directly take it and interpret it. So you have this scripting that's available, so you can have different pulses of your biasing, and then you can make sure where to read and where to write. So you can have more complex signals, so you can have this kind of different, so you can have, this is your biasing, so you can have this kind of typical sawtooth pattern, which is well established in the literature. So each individually, if you look inside this triangle, there are multiple square waves at different voltages, and then it kind of flips, and then you read it at certain point. In this case, it's read at 0 voltage. So you can also read it at the right voltage, but yeah, so this is what it is. Yeah, so you can have that. You also now, I mean, this has been there, but this is less often used in the academic world or studies, is to use the PFM capability of the sample to actually change your polarization of the sample of the domains. So you can use it as a lithography tool. So you apply a high enough bias so you can pull your sample normally. Then you can, when you read this, after polling, you read it, you can get this kind of amplitude and phase signal, but it won't be visible in the topography, right? Because it's a PFM data that the surface is pretty flat. So you get this PFM data. So here is another example. So here is the topography you can see. So you can, there are different stripe domains are created. So applying +5 volt, -5, +5, -5, etc. You can see also the phase that's there. Okay. So another example. So this is trying to push it how close you can. So you can have different kinds of patterning. So in this case, a different periodicity, different dimensions, so either like a rectangle or circular, and different diameters, and yeah, so etc. So you can have your fun with it. So any patterns you want, you can do it. So more interesting things are, of course, to combine your PFM data with your current data or your potential data, which are direct electrical measurements as opposed to electromechanical piezo responses. So you have the height, like you always do. You can get the current data and the phase data, right? So the current you can see in this case is very, very low current. So you need a high amplification. So it's called tuna amplifier we use there. And you can get the current data simultaneously. You are getting the PFM phase as well. So this is same at you are doing at higher and higher speeds. So conventionally, you are doing maybe 1 hertz or 2 hertz all the way to 100 hertz, right? So you are able to not only get more complex data, but you can get them faster without significant loss in the resolution. Of course, there is some loss here, but it's still, you can make out things even at 40 hertz. It's pretty good. Right. So similarly, we can expand the PFM with kPFM data or photoconducting AFM data. In this case, the researchers are studying methyl ammonium lead iodide perovskite thin films, and you can see the in phase of the PFM data, and you can also see the photoconductive response and the kPFM response for the same material. All right. So now comes the more fun parts, which is called the DataCube PFM. So like I mentioned before, conventionally PFM is done in a contact mode way. That means you're going to have all the drawbacks that come with a contact mode imaging. And we also mentioned that to avoid or minimize the electrostatic contributions to your PFM data, you would ideally like to have your DC match work function and also to have a stiffer cantilevers, right? So that is not also good when you're doing the contact mode PFM. So the DataCube PFM is more like a spectroscopy. So you come with your cantilever, you come engage it, and while you are engaging, you do a PFM, and then you keep it retract and do it multiple times. So there is no lateral movement of your cantilever on the sample, completely avoiding the friction forces, thereby avoiding the tip of the sample damage. And you are going to get a very rich set of data, right? So it's called the data cube because you have a cube of data. So let's look at these graphs first. So you are very far away from your sample, then you come apply a fixed force. You can maintain the force, right? And while the force is being maintained at a fixed level, so maybe let's say 1 nanonewton or 2 nanonewtons or whatever, you can do multiple things. Either you can sweep your AC frequency, or you can change your bias, or you can sweep your voltage, and then you can do the measurement. So you can and every pixel in your data is gonna be basically like a spectrum, and you can have images also. So you have like a cube of data, right? So you have the FT curve, and then you can have a 4 slice. You also have the electrical spectrum. You can have the electrical slice as well, and you can see what's interest here. In this particular case, they are sweeping the voltage. It could be the sweep of the frequencies as well. So it's really a lot of benefits here. So you can use low force, very good for soft and fragile samples, like ferroelectric polymers, for example. You can get correlated mechanics because you are getting a force curve at every pixel along with your electrical spectrum. That means you can get your modulus, addition, and other mechanical properties as well. And yeah, you get a spectrum at every pixel, which is in itself gives you a lot of information on your sample. So here is one such example. So what you see here is a multiple slices. So basically 6 different slices of amplitude and 6 different slices of the corresponding phase are done at different voltages. So you come and contact, apply a fixed force, and then you are doing a voltage sweep. And then we have plotted 6 such slices. So from 0 volt to -6 volts, and you're looking at how the phase is changing or how the amplitude is changing during that, right? So similarly, you can actually take the data, and then you can, we have drawn in this case a line, and across this line you can see how the responses, amplitude responses, across this particular cross-section line that we have drawn. And you can also see there's different amplitude responses of different points there along the line, right? So this is basically another way to represent such a data. So you have the amplitude as a function of the XY of your sample. On this dimension, you have the different DC biasing that we did, and you can have different slices. So either if you slice this this direction, that's what we saw here. So basically, like you're looking at a particular section of the amplitude, how across the voltage barriers, and you're looking in this way. You're looking at a area map of amplitude at particular voltage point, right? And similarly, you can also get the multiple hysteresis and the amplitude points as well. So you can understand your property, like, so yeah, you can take a section, and then you can look at how this switching bias is and how many regions are there, so you can understand the different properties of your materials as well. So here again, so this is a video that we have done for the for a similar material, lithium tantalum oxide. So you can see, right, so sweep across the bias, and then this made it into a video of the phase and the amplitude change. Okay, so like I mentioned before, yeah, you can sweep the voltage that we saw before, but you can also sweep the frequency response of the material. So here, again, you do the same thing. You come very far away and you apply a fixed force and you maintain the force. And then during the force, you are doing a sweep of the frequency. And at some point, you might hit the contact resonance, and then you can see that point resonance point there. So you can see here, so this peak that you see that's constantly moving here and there is the resonance point, and then you can see this in response to the scanning. So as you move from one location to the other location, the contact resonance shifts, and by doing a sweep of frequency, we can track it, and we can plot the PFM amplitude at this resonance frequency, right? So we are constantly tracking that, and we are also plotting the addition to understand a little bit more of your sample from the mechanical side, how the addition behavior changes between your tip and the sample. And again, this is important to mention. So you are going from measure, go up and measure, go up and measure, etc. So there is no lateral dragging of your cantilever. So there is very little tip wear. So this is not a contact mode that you're doing. You're more or less doing like a tapping mode at very low oscillation frequencies. So this is one of the real powerful. So everybody knows when you're doing the measuring at the contact resonance, also your PFM signals are enhanced. So you get a very high quality of signal to noise ratio, and then you are doing this across the sample. So here again is the point here. So you can see the frequency ramp is changed from 250 to 400 kilohertz in every pixel. So at the when the force is maintained at say 2 micronewton or 2.2 micronewton in this case, it's held for about 100 milliseconds. And every pixel it goes through this, and every pixel you can see they sweep the frequency of your AC bias from 250 to 400 kilohertz, and you can see there are these contact resonance peaks that you get as you sweep. Of course, this is plotted as time. The frequency is changing, so the frequency is changing linearly like this, and you're gonna get, depending upon which location of the sample you are, you're going to get contact resonances, and that's what we are using to do the measurements. So sometimes you get more than one peak, we can use something. So here is another nice example. So here you get the height data, the addition data, and you can also see we can calculate the quality factor, the Q of your PFM response, the CR amplitude, the contact resonance amplitude, the contact resonance frequency. So you can see depending upon where you are, the contact resonance changes a bit, right? It changes from 312 to 322. So, and then also the PFM phase response at that contact resonance frequencies. So you can see this kind of very nice, rich data set you can get from one single measurement. So these can give you a lot of interesting ways to look at your sample and probe them, right? So yeah, so this is, you can do different ways and different speeds. So just to give you some ideas. So if you're doing at 6 seconds, 6 milliseconds dwell time, you are doing 122 hertz ramping. The spectra per second, you can get about 69 spectra, right? So roughly to take about 128 pixel by 128, it takes you about 4 minutes, which is not a lot of time, right? But the more time you stay and then you want to do a larger and larger sweep, of course, it takes a little bit longer time. But even if you're doing 50 millisecond dwell time, you can still do it in 15 minutes. So conventional AFM imaging, if you do tapping or contact mode, you are somewhere around 5 minutes or so, right? Depending if you're doing it 1 hertz. So this is gives you an idea in terms of the time scale we are talking at. This is not really like forever measurement. So we are talking 10 to 15 minutes to get a complete understanding of your sample from different dimensions, right? You get a whole DataCube. So to play with, you can get this kind of rich data set. So like this one, this data took about 16 minutes. So you can get the complete phase and the amplitude response across a frequency, right? So you can measure off resonance, on resonance, you have the whole set here. And you are tracking the frequencies also as it goes by. So this is a similar set of data by our collaborator Langenberg from Cornell. So this is, you have the height image and you also have the addition and this contact resonance amplitude of the sample. So now we saw how we can get nice signal and you can get richer data set. But once you want to do quantitative data, then it's very important to ensure that the electrostatic components are absolutely zero, right? So the one way to do this is to do, I mean, the basics of PFM. I think many of you know this, so I will not go into detail. So you can record the response, like I mentioned, when you apply a bias. you can record it at the top of the bias or when the bias is 0. So this is on field. But classic PFM that you do is always on field. So when you apply the bias, you actually do the measurements of spectroscopy. That means you have a lot of possibility of a large electrostatic force contribution. With the scripted PFM, I talked briefly about it earlier. So you can you have multiple like square wave functions you can apply, whatever functions you can apply. You will have this on field, so you can record the PFM spectra when the bias is non-zero or something, and you can have a read voltage, which many cases can be 0 volt, but sometimes it can be a different voltages depending upon the work function difference you think you have between your sample and the tip. Ideally, like I said, when the DC bias that you apply is negative of the work function difference, then you are going to get the response that's purely PFM, and that's quantitative, right? And that's what we would like to achieve with the switching spectroscopy. So we just don't want to do like this and then set the read voltage always at 0 volt, but we also want to be able to do read voltage at different voltages and have the biasing at different points as well. Yeah, so this is the same concept here. So you have the electrostatic force that's acting on your cantilever, not only at the apex, but also at the entire length of the cantilever, right? So, so what we want to do is measure the hysteresis loop without the electrostatic field artifacts. So what we are going to do is we are going to have multi-segment scripts with the write and read steps. So the write steps are, you see in the blue, the read steps are the red one. So you have 5 different read steps. So some are set at different voltages. So this one here, and then 3 is here, 4 is there. So you have some at negative, some are positive read voltages, and you get a PFM hysteresis loop is extracted. The hysteresis loop where the samples work function is the more artifact-free one, and that's the correct one quantitatively speaking, and that's the one that should be used, right? So we have this implementation that makes it very easy. So now you can generate thousands of segments with 10 or less parameters. So it's very easy to set up and run. So I have a small video that I can, yeah, so maybe let me play this video first. Okay. So maybe before that, let me explain what do you see for here. So this is the software interface of our nanoscope control software. So this is in the PFM work view. And what you see here is called the mirror view. So you have the camera here, and on the camera you have identified a location and you got the data, and this is the data. This is, I think it's PPLN, periodically poled lyodium nitrate one, and you have some, it's poled, so you have negative, so pointing upwards and pointing inwards polarization. This has been biased this way and made this way. So now this is what you see, and you can see these are the recorded images, and this is where you set your scan parameters, and these are the different channels that's being recorded at the same time, which includes the height, the error, the amplitude, phases, etc. Right. So let me play this video and then narrate it as it goes. So you go there into the tools, you select the switching spectroscopy, so you get this view. So it's very simple. So you can say what's the force you want to set at to do the recording. So, you know, piconewton, how many ever piconewton, so 9 nanonewton, whatever. And then you are going to set how much the voltage sweep should be, right? So you can set it from -10 to 10, and you can start it from 0, or you can start it from -10 and then go to 0 and then etc. And then you can also record during the write cycle. So you set how many writes you want. So in this case, it was set at 1. Then the read voltages, it's not necessarily have to be 0. So we are setting 9 different levels of read voltages from -6 to 6, right? So these red lines you see, these are your read points, and these are set from -6 volts to +6 volts with 9 different levels, right? And how many points you want to, how many data you want to record at every read voltages, and how much should be the segment durations can be set here. So I say 2, I want segment durations of this many milliseconds. You save this file, right? Then now what you're going to do is, this is the DataCube way, sorry, mirror view way. So you can just select from here how many areas you want to do it. So you can do that. So you just draw an image there, and you say, okay, I want to do it at this point. Select the script that you want to run there that we just made. Okay. All right. So now that's set. So that whatever script we did, and we can choose as many points as we want to do run this script set. So you select, I want here, 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 or you can select the array. So if you can make a 10 by 10 array, so yeah, I can do a 10 by 10 array here. There will be, yeah, that many. So each point is the entire script that we are running. So each is quite a lot of data. So think about it, it'll be several megabytes of text. So you can think the amount of data that's being collected at every point. So then you do that and then press play. That's pretty straightforward. So you can see that it is doing what we've done, set it to do. So you have different write and read voltages that's being done there. So after each point, it will go to the next. So it will do these 3 points first and then do the array. And that's how it is done. And this video you see is in real time scale. This is not fast forward or something. This is roughly how long it takes to do the measurements. Yeah. So one measurement, it takes about few seconds. And once you do that, you can get the data in your analysis software. There you go. Yeah, it takes a little bit time to load. There's a lot of data. So this is your data. This is your read and write voltages, and the pink one is the amplitude corresponding to it. And each of them is the data, and you can plot them into images, or you can analyze them as text, however you like. So you can just scale it a little bit, and then you can zoom in. Like if you zoom in, you see this read and write points, and these are your amplitudes at that particular point. So you have these two read cycles and the write cycles. Yeah. 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 Okay. So now we can do some old analysis. Maybe two. Yeah. So that's the concept that I wanted to show you today. Yeah. So you get the idea. The switching spectroscopy is of course a very complex technique, but with the new implementation is pretty straightforward as to set how many runs you want and how many areas you want. And once you have done that, you can identify which is the one that's the correct one, and you can get this nice piezoelectric loop. So we can have, you can run the data through our analysis software, but you can also run it through a Python script like many of our customers like to do. So you can have, we have our own Python scripts as well that we can give you. So you run it and you can fit different key parameters like saturation level, remanence, coercivity, hysteresis area, etc., etc. So you have a full data set of force distance curves, you have a full data set of electrical properties with the frequency sweeps, and you can get different thing. And by doing the switching spectroscopy and having a different levels of read and write voltages, you make sure that the electrostatic components is turned to zero, and you can really do some quantitative piezo response studies, right? So that's that. So this is a PFM in liquid. It's a little bit more like a conceptual study. So there is a publication that we did with published in Nanotechnology. So PFM being electrical measurement is conventionally done in ambient, and there has been a problem doing in liquid because you have a conducting tip, right? So the way we are able to come is like of course, we can have a tip that's isolated, only the apex is conducting and the rest is all passivated, so it doesn't short everything. But these kind of tips are so delicate, and there's been so far, people have been able to make the tips, but not able to use them in a straightforward way under liquid, simply because they are fragile and the force control with the systems have been very poor. And with our DataCube and peak force tapping and these kind of implementations, we can now handle these kind of complex probes. And there is a wide range of interest, especially from biologists or people even doing electrochemistry and photovoltaics for or hydrogen water splitting. So to understand how the behavior or electrical behavior is under a liquid condition. So in this paper, they did with different liquids and air and etc. So this is PPLN in Desane, the data that's corresponding here. So you can see the Q factor, the frequency, the amplitude. The amplitudes are of course sweeping, and you're trying to do this the contract resonance point that we are sweeping the frequencies here, right? And then PFM phase at resonance. So that is the right there. So that's pretty much all that I wanted to cover. I also recommend you to go through our webinar that's online. These are on-demand webinars. So this is called Advances in Piezo Force, where we actually also have a live demo that is recorded and available there. You can get some idea about how the DataCube is run, and so I wanted to show the video, but we have some technology problem that I'm not able to do it with the audio. So this is the summary of what we have done. So we have seen some conventional PFM features like vertical lateral imaging, spectroscopy, some simple switching spectroscopy, and then we talked about correlating PFM with the tuner kPFM data, and then do this DataCube PFM at contact resonance and off resonance, and also do this switching spectroscopy in an in-depth way, which is not been possible so far, right? And now with our latest system, this been come to a commercial system. So that's it from my side. So I will now open the floor for questions. If you have anything, you can put on the chat window, and then we can hear you. Teja, do you see any questions in the chat window?
Yeah, nothing as of now.
Huh.
So I request the attendees, if you have any questions, please let us know. We can have an interactive session right now.
Yeah, Yogesh, there is one question from Rashik Rashid Malik. Is asking, is it possible to obtain depth profile of Piezoresponse in any sample?
What depth profile?
Yeah.
I don't know what it means by depth profile. Can you clarify that, Rashik? Okay. I'm not sure I understand your question very clearly. Depth profile of a piezo. So you will get your topography, which is your fundamental for AFM. Nothing happens without it. So you will get your cross section. If you have any features there, like nano features, you will capture that in topography, and you can also capture your piezo response at the same time. Yeah, I hope that answers it.
Yogesh, one more question from Mr. Shumit Chaudhary.
Mhm.
How to nullify the work function at artifacts while PFM measurements?
Yeah, so that is the whole concept for the switching spectroscopy. So that's what we do there when we did the switching spectroscopy. What we are doing is two things, right? So you are making sure that you are not reading when you apply when your DC bias is non-zero, and thereby contributing to your electrostatic problem. So you're doing the reading at different voltages, and by making sure you're reading at different voltage levels, that when the DC is zero, but also maybe sometime negative, positive, etc. So you set the different ones so that you make sure that the DC bias you apply is negative of your work function. So if you know your work function difference, that's great. If you do not, then you can read it at that voltage, negative of that voltage. If you do not know, then you can read at different voltage. And that's the whole concept of the switching spectroscopy. And by varying the voltage up and down, you make sure that you are not charging the sample, and by adding to the problem, that's why you see that the pulse is going up and down and up and down. So make sure that there is no charging effects there on the samples as well. Okay.
Yeah.
Yogesh, one more.
There's another question.
Yeah.
Yeah, I can see, Saradi,
Yeah.
from Mr. Anand Babu. How to avoid the electrostatic responses in PFM? What is the superiority of switching spectroscopy over others?
Okay, so there's a lot of interest here. So the electrostatic response, if you see simply, there is three components there. So one is the DC bias that you apply. The other is the work function difference. So it's DC bias you apply minus the work function difference divided by your spring constant, right? So it's inversely proportional to the spring constant of your cantilever, and directly proportional to this VDC, the DC bias minus the work function. So if you are really interested in making sure that you do not have any electrostatic components there, that means you can either make your VDC and work function difference to be zero. That means your VDC is opposite of your work function difference, or you have your K so high that the difference doesn't make any impact, right? Or you can do both. But if you make a very high K, that means you decrease your sensitivity in measurements, right? So it's also plus and minus there. So in conventional way of doing it, like, conventional PFM, where you apply a fixed bias and then you're reading it in a contact way, there is only so much you can do to avoid it. Actually, there is not much you can do. So there's always there. So you just do not either consciously know it, or you do not know what's the contribution to it. So the only way to avoid it is to do a switching spectroscopy. The simple switching spectroscopy, the implementation would be, okay, I apply different pulses, and then I have a right voltage, which is at something, and then I read it at different points, right? Then I look at the piezo response that way. It works maybe in some cases, but not every time. It is not perfect again. So that's why you have this complex way that we showed you. So let me pull that on again. Yeah, so I'm not sure whether you can see this. So yeah, so what you are going to do is you are going to create this kind of a complex biasing function. So this is how you bias. So the blue one is the voltage you apply, and the red dotted lines are the points where you actually read. So you actually read at on field, which is at the top of the blue one, and off field, that's at the lowest point here. So this on field, you have one or two measurements. Maybe in the read cycle, you will have more measurements. So this is called the write and the read cycles. So then you have set up a different read point. So 0, let's say here -1, -2, whatever, and then +1, +2, right? So at some point, if you make sure that this is done correctly, at some point your VDC is exactly equal to your negative of your work function difference. Then you can do that. So that's the one way to do it. Yeah.
Thank you. The next question is from Mr. Pankaj. Is PFM full proof of ferroelectric behavior, since some non-ferroelectric also gives
Oh, sure.
ferroelectric interpretation like TiO2.
Yeah, sure.
And
that
he
can happen.
continues. Yeah, he continues the question. Since PFM can read either 0 or 180 phase, can we use it to read in between phase 2 also?
Yes. There is no limitations that it has to read only 0 or 180. So you can read. So if you have a domain that's completely normal to the surface, you will read 0 or 180. It flips. If you have a domain that's pointing arbitrary directions, then you will read that phase. It's not always 0 or 180. But some of the standard samples we would do it is designed that way. It is that way. You can read any phase in between. Yeah, so there are, of course, non-ferroelectric materials that also exhibit PFM, and that has been some controversy. So before, if you can say, I see a PFM, that means it's a ferroelectric. That's not always the case. And sometimes I also think that some people claim that they have a piezo response. Just is usually electrostatic response. So by doing this, you eliminate the electrostatic effects, and what you see is a piezo response. And it's just a piezo response. We are not claiming it's ferroelectric. That's for the researchers to input, right? You have more idea about your sample than we do. And this is definitely one component towards establishing a material ferroelectricity.
I think last two questions. One is from Mr. Pranav. What is the minimum area size where PFM can be done?
Is the same limit, basically no limitations. Your conducting tips, you can now even find, if you have like a diamond tip, maybe like 1 nanometers, so you can do as small as you want. So theoretically 0, right? It's just 1 point, right? If you do 1 point, that's 0, right? That's not really a scan. So if you do 2 points, then you got that's the minimum, right? 2 pixels. So you can see, so you have 2 spectra, that's the minimum one, or area if you have to design. But if it's actually anything you want, you can set it there.
Yeah. So last question from Munshi. What exactly does contact resonance represent?
The contact resonance represents the resonance point between your cantilever and the sample. So you come with your cantilever, you touch your sample, you are in contact. And when you are sweeping with different frequencies, at certain frequencies, the energy is transmitted better. That is due to the contact dynamics between your sample and the tip. And this changes from point to point, depending upon your sample material and also the topography change there. And that's the contact resonance. And when you are doing the PFM data measurement, imaging at contact resonance, the signal is very, very good and very enhanced, right? Basically, because it's a resonance point. And that's why when you have a weak PFM material, people like to do it at contact resonance, the imaging. And mind you, your quantitative data, like if you're doing spectra or something, you shouldn't do it at contact resonance. You should be far away from the contact resonance for quantitative data. But if you want to image, then you can do it at a contact resonance point.
Well, I think we are on the verge of closing this webinar. I sincerely thank you, Dr. Yogesh, for introducing great insights about the latest advancements and implementations from Bruker, especially focusing on PFM. That was a brilliant content, and I believe this webinar had been very informative, and he has given great insights, experience to all the attendees with respect to this topic. Once you leave this webinar space, you will be automatically en route to a survey poll about this webinar. So please take your time and try to fill it, which is very crucial for our internal assessment purpose. Thank you for all your time, and hope to see you soon in another webinar. Thank you, Dr. Yogesh.
Thank you, everyone. Bye.
Bye-bye.